Hello everyone. Today I'm going to talk about this paper in ICPP 2022, HARL, Hierarchical Adaptive Reinforcement Learning Based Autoscheduler for Neural Networks. This work is under the National University of Singapore and Neuron Singapore. To talk about the autoschedulers, first we need to talk about what is scheduling. Scheduling of a tensor program is to speed up its implementation by tuning the parameters. To talk about the parameters, let's read an example. For example, matrix-to-matrix multiplication. It is usually implemented with multiple levels of tiles. So the tile sizes, the loop structures, all of these things are called the parameters in the scheduling context. The tensor program scheduling usually improves the performance significantly. For example, for a Mobile Light V2 on CPU, it can speed up by 10 times after searching for the good schedules. And this is compared to the PyTorch implementation, which already utilizes some vendor-provided libraries like Intel 1DNN. So it is a large improvement after the scheduling. However, the scheduling normally requires tremendous engineering efforts. So for the matrix-to-matrix multiplication example, for a 1024 times 1024 multiplication, it usually contains as many as 180 million schedules. And to brute forcefully search inside this large search space is very time consuming. So autoschedulers are developed to search in this schedule space wisely and without human interference. For the autoschedulers in the current literature, I will split them into two categories. First is the statistical autoscheduler, then is the learning-based autoscheduler. For statistical autoschedulers, they normally apply the traditional statistical optimization methods like the simulated annealing or evolutionary search. For AutoTVM, it is template-based, which means that it needs user to input a template to help make the search space smaller. For learning-based autoscheduler, they normally apply reinforcement learning-based algorithms. This is because reinforcement learning estimates the best movement in the next step in a global view so that they can win at the end. This is very similar to parameter modification in autoschedulers. In each tuning step for autoscheduler, they estimate the best modification direction also on a global view, not greedily, so that at the end of the tuning steps, they can reach the best performed tensor program. We have two examples of reinforcement learning-based autoscheduler. The first is Chameleon, which replaces the simulated annealing in AutoTVM to reinforcement learning-based algorithm. So Chameleon is also a template-based autoscheduler. This is because the deep learning-based reinforcement learning is most suitable for parameter modifications in a fixed loop structure. It cannot well handle the complicated tensor operator combinations because it needs to decide the loop structures alongside with the parameters. And for flex tensor, it is not template-based. This is because it has a very general template that can cover a large variety of tensor operators. Still, it cannot handle the complicated combination of multiple tensor operators, so it cannot optimize end-to-end neural networks. To help explain our solution to optimize the autoschedulers, we will first need to have a problem definition for general autoschedulers. So firstly, we have an optimization target neural network as input to the autoscheduler. Firstly, we can split this whole neural network into multiple subgraphs to divide the problem. So in each round of optimization, we will pick one subgraph N for optimization. Each subgraph actually is a combination of multiple tensor operators. So its implementation structure, also known as templates with parameters unsettled, is defined as a sketch U of this subgraph. One subgraph can have multiple implementation structures, so it can have multiple sketches. And this is to disentangle the decision of the loop structures with the selection of the actual parameters. Each optimization round optimizes on a specific subgraph with a specific sketch. And when talking about this procedure, current optimization round is numbered as T. Within each optimization round, different schedules are tuned step by step. So in this phase, the specific parameters are settled. Each tuning step is numbered as T prime, and the current tuning schedule is denoted as S. So next is the solid example of the above procedures. Here is the input neural network we are going to optimize. And at the current optimization round, T, we select this subgraph to optimize. So in each optimization round, we will select the subgraph N with a certain probability. We denote it as pi t. And we denote the total number of optimization rounds allocated to this subgraph N as Tn. For this layer, the implementation, it looks like this. So the C is a matrix multiplication result, and D is the result after it adds to a bias, and at the end, the E is the activation result of ReLU. After selecting the subgraph N, we will select one specific sketch or the loop structures of this subgraph N. So we select it with a specific probability denoted in this form. And we can see that in one example of this sketch, all the parameters are left unsettled, and they will be determined in the next step. After selecting the specific subgraph N and its sketch U, we need to decide the specific parameters allocated to these placeholders. And firstly, we will sample a batch of initial schedules from this sketch U. We can see that the parameters are randomly settled for these initial schedules. And for each schedule, they independently go through the tuning steps. For example, for this schedule, on the dimension J, it will modify the two tiling loops. So their products are still the same, but the tiling size allocations are different for these two schedules. So we call this the tiling size modifications. And it tunes the schedules from the T prime minus 1 to ST prime. We denote the probability of this transition in this form. For each initial schedule, it has a search path for it to modify the parameters. We call this search path a schedule track, and this is the schedule track I, and this is the schedule track I plus 1. So after a total of TIN tuning steps, for each schedule tracks, we will get a final output schedule in the current optimization round. So after introducing the general problem definition of the autoschedulers, here we can summarize the problems of the current autoschedulers. So firstly, for the statistical autoschedulers, the optimization decisions are either greedy or heuristic. And here I answer as an example in this table. You can see that the subgraph selection pattern is greedy because it selects the subgraph based on the previous observations and selects the subgraph with the historical biased performance. And for the sketch selection, since each sketches of the subgraph N are independent to each other, so it uses a heuristic uniform distribution. And for the schedule transition, it also uses the uniform distribution. And for the learning-based autoschedulers, instead it will use the reinforcement learning-based algorithm to select the next schedule. So this can largely improve the search efficiency. However, for the subgraph selection, it is not supported because the deep learning-based reinforcement learning cannot handle the combination of tensor programs well. Another drawback of reinforcement learning-based autoscheduler is that they allocate a fixed number of tuning steps for all the schedule tracks. We believe that this will result in wasteful tuning steps. To verify the above-mentioned drawbacks of the statistical autoscheduler and the reinforcement learning-based autoscheduler, we conducted a few experiments. For example, the first one, we want to verify that the greedy subgraph selection in statistic autoscheduler will waste the optimization rounds. This figure is conducted on BERT. Subgraph 1 is the most time-consuming subgraph, so it is allocated with most of the optimization rounds. And the sketch bars means that they are the last 1% improvements. And we can see that a lot of optimization rounds are allocated to subgraph 1 for this 1% improvement. We believe that if we can allocate this large amount of rounds to subgraph 5, then we can get a lot more performance gains. The second figure is used to verify that the uniform next schedule selection procedure makes the tuning steps inefficient. We conducted an experiment that collects a bunch of schedules. For each of the schedules, they can be tuned to another schedule. We uniformly selected these next schedules and test the performance improvements on them. And in this figure, the improvements performance distribution are plotted on it, and as expected, most of the improvement is around 0. And this is an inefficient tuning strategy. For the reinforcement learning-based autoschedulers, they have the problem of fixed length tuning step for all the schedule tracks. We record the position of the best performed schedules along each schedule track. And if it is at the middle of the schedule track, it is allocated in these buckets. And from this histogram, we can see that most of the top performed schedules is around the early stage of the schedule tracks. And for the remaining of the schedule tracks, they are allocated quite uniformly. And we want to have an improved tuning step allocation that can make most of the top performed schedules appear at the end of the schedule tracks. This is the overview of our HARL system. From this figure, we can see that it matches the problem definition of the general autoschedulers. The first block represents the subgraph selection process using the multi-armed bandage-based reinforcement learning algorithm. And for the sketch selection, it also uses the same problem modeling. And after selecting the target subgraph and the sketch, we start to film the parameters using the actor-critic reinforcement learning algorithm. So in the following slides, I will explain the details of the HARL system. There are high-level decisions for the subgraph and sketch selection, and low-level decisions for the parameter modification. So for high-level decisions, we use bandit-based reinforcement learning. The subgraph selection and the sketch selection problems are very suitable to be represented as a non-stationary multi-armed bandit problem. This is because the number of subgraphs in a neural network is a fixed number, and every time you select one subgraph from it, the performance gain may change. Because one subgraph, after optimizing it for multiple rounds, it may not be beneficial anymore to continue to optimize it in the next few rounds. So this is why we use the non-stationary MAB problem modeling. For the solution to the non-stationary MAB problem, we use sliding window upper confidence bound. So this is shown in equation 1. We can see there are two terms. The first term represents the performance estimation when selecting the target subgraph or sketch, and the second term represents the exploration property of the reinforcement learning algorithms. So we can see it is inversely proportional to the square root of the number of optimization rounds already allocated to the target subgraph. So if one subgraph has already been allocated with a large number of optimization rounds, although our estimation on the performance may be high, we may not select it in the next round of optimizations. For the performance estimation of the subgraph and for the sketch, their formulas are different, and the details can be found in my paper. So for low-level decisions on parameter modifications, we use actor-critic-based reinforcement learning. As I have already discussed in the section about the chameleon and flex tensors, we know that the deep learning-based reinforcement learning is suitable for parameter modification. That's why we use it in this stage. Firstly, let me introduce the parameter search space shown in this figure. The nodes represents the states in the reinforcement learning language, and they are actually schedules in the context of a scheduler. And for the edges connected between the states, they are the actions in RL language, and they are the modifications of the parameters from one schedule to another schedule. In this table, it shows all the parameter modifications are used in this work. So there are tiling modifications, compute at location modifications, the parallel loop modifications, and the auto unroll modifications. The last one is the reward function. We can use the actual measurements of the schedules to represent the reward of the states, but it is very time consuming. So to save the time, we use a lightweight cost model to learn from the previous actual measurements and use it to predict the reward for each of the schedule. For the tuning steps, we split them into two phases. The first phase is the parameter modification phase, and the second phase is the top K selection for actual measurements. And for the first phase, the parameter modification, we firstly randomly sample a batch of initial schedules and put them into the actor-critic network for the forward path. This whole process is called an epoch of the batches in the reinforcement learning language, and they are also called schedule tracks in the scheduler's context. In this process, we use an adaptive stopping module to early prune the batches, and they will be explained later. In the meantime, we also use a cost model to estimate the reward function. The rewards are used for the training of the actor-critic network in the backpropagation path. For the second phase, which is the top K selection of a small proportion of the visited schedules for actual measurements, we follow the following workflows at the end of an epoch of batches. So firstly, we will predict all these the rewards of all the schedules using the cost model. Then we will select the top K schedules with the best rewards. We send these schedules to the manager for the actual measurements, and the results will send back to update the cost model. Next, let's talk about adaptive stopping used in the schedule tracks. So there are two options. First is the fixed length parameter search. This is used in the flex tensors, as we have mentioned in the previous slides. So for the whole schedules, all the schedule tracks are searched to the end, no matter how well performed the schedules are. Inside the boxes, the number represents the performance of the schedule, and the higher the better. We can see for the schedule tracks T1, T2, and T3, they have already achieved their best performed schedules at the early stage of the schedule tracks. However, they are still searched for a long time. Our motivation is that why not we allocate these wasted tuning steps to the schedule tracks that has higher potentials, like T4 and T5. So this is our idea, the adaptive stopping. It uses the advantage function in the reinforcement learning context. So firstly, we have a window. Within this window size lambda, the schedule tracks behaves like the fixed length search. But after that, all the schedules will be sorted according to their advantage values. So the advantage value can be treated as a summarization of all the schedules originated from this schedule, so which is a good representation of the future of this schedule track. We think that this perfectly matches our demand. And for the schedule track T4 as an example, so after the adaptive stopping procedures, it reaches the much higher performance than in the fixed length search, which indicates an efficient search algorithm. So up to now, we have introduced all the technical details of our HARL system. So next, let's talk about the experiment results. Firstly, the setup. We use the CPU and GPU as our testing platforms. For the baselines, we use the answer, and also known as TVM autoschedulers. For the implementation of HARL, the cost model we used is a lightweight XGBoost model. And for the reinforcement learning model, we use the proximal policy optimization. For the implementation details, you can find it in the appendix. For our experiments, we conducted the optimization comparisons on two kinds of tensor programs. The first one is optimization on tensor operators, and the second one is on the whole end-to-end neural networks. For the tensor operators, the workload is on two computation-intensive operators. The first one is the generalized matrix multiplication, and the second is the convolution operators. They are conducted in different settings, so jam small, medium, large, and the 1D, 2D, 3D convolution operations. The details and the settings can be found in the appendix, and the batch sizes is 1 and 16. For the search settings, all the experiments for the tensor operator comparisons is conducted on CPU platform, and each of the operator is optimized for 1000 actual measurements. We also make the baseline and HARL contain the same amount of visited schedules for fair comparisons on the search efficiencies. For the metrics, we use the final performance of the output tensor program and the search time. For the search time, it is the time consumed by the autoschedulers to find the tensor program with a performance no worse than the final output program of the baseline. All the metrics are normalized to the values between 0 and 1 for clearer comparisons. This slide shows the experiment results of tensor operator optimization comparisons. The first figure shows the performance comparison. We can see that HARL can outperform answer on all these computation-intensive tensor operators. And for the search time, HARL uses much less search time than answer to find the similar performed tensor programs. This slide shows the application study of the tensor operator optimization. The first figure shows the records of using different optimization methods. It shows the methods using answer, using the hierarchical RL, which is a HARL implementation with fixed length search, and this is a HARL implementation with adaptive stopping search. We can see the hierarchical RL still outperform answer thanks to its MAB-based RL search on subgraph and sketches. And for adaptive stopping, it largely outperforms the other two methods. And in this figure, it shows the comparison between the fixed length and the adaptive stopping search methods. For the adaptive stopping, most of the top performed schedules appeared at the end of the search path, which means a savings of the tuning steps. For the experiments on neural network optimization, the workloads we select the ResNet50, MobileNet V2, and BERT models. They are quite representative in the fields of CV and NLP. For the search settings, they have different measurements. We use the same settings as what is used in answer, and all the models are tested on CPU and GPU platforms. Here, the first figure is the performance comparison among all these models, and the J here represents the experiments shown in the GPU platform. We can see HARL can outperform answer on all these models, and for the search times also. This slide shows the application study of the neural network optimization. This table breaks down the subgraphs in the BERT on CPU platform. And we can see the top 5 subgraphs contribute to most of the execution time, and they are allocated with most of the optimization rounds, so they get most of the speed ups. And for the theming of the search paths, we conduct the experiments on two settings. The white bar represents the HARL without subgraph MAB, and the brown bar is the one with subgraph MAB. We can see that MAB is able to detect the overly allocated optimization rounds to this subgraph. Instead, it allocates more to the softmax subgraph. And this brings a larger speed up on the overall neural network. Okay, this is the end of my presentation. Thanks for watching until the end.